Let's solve the following system of linear equations. 2x minus y plus 3z equals 5. 3x plus 4y minus 3z is equal to negative 6. And x plus 2z is equal to 6. And there's many different ways to do these problems. But I am going to do an unusual way. I'm not going to do this like you did in beginning algebra or intermediate algebra. I'm actually going to solve this mimicking a procedure called elementary row operations. The first thing I'm going to do is actually label my equations. I'm going to label them like this: equation 1 being the top equation, equation 2, and then equation 3. So what we're trying to do is find values for x, y, and z that will satisfy all equations simultaneously, and it will make all the equations true all at once. That is the goal. We're trying to find the missing values x, y, and z that will actually satisfy all three equations. I am going to mimic a procedure that you may end up learning later on that involves matrices and elementary row operations. So the first thing I'm going to do is I'm going to switch equations 3 and 1. And then we'll rewrite the system in this order. X plus 2z is equal to 6. And then equation 2 is still equation 2. And then now the equation 3 is simply 2x minus y plus 3z is equal to 5. Now you're probably wondering, why did I do that? Let me rewrite the first equation really quick. So now this is a little bit different. And I'm going to relabel this. This is now equation 1, equation 2, and this is now equation 3. What I'm going to do now is actually temporarily eliminate x in two of the equations. And the way I'm going to do that is I'm going to apply negative 3 times equation 1 plus equation 2 hang on just for a sec here. I'm going to do that. And we're also going to use negative 2 times equation 1 and then add it to equation 3. I'm going to keep equation 1 where it is. So equation 1 is still going to be called x plus 2z equals 6. Let me move this slightly over. Move this over here. It's actually much easier to do this with matrices, but we are not there yet. So I'm trying to reorganize my paper here. Need this a little bit higher, right about there. Okay, a little bit more to my right. There we go. I think I finally got the spacing right. I apologize. I'm not used to doing this without matrices. It's much easier with matrices. And this is going to be something else. And this is going to be something else. All right. What is negative 3 times equation 1 plus 2? What does that mean? I'm going to do this once off to the side. So I'm doing a lot of steps in my head. Negative 3 times equation 1 plus 2 really means you're going to take negative 3x plus, well, let's do minus 6z is now equal to negative 18. So that's negative 3 times equation 1. Now plus 2, well, what's equation 2? This is equation 2. 3x plus 4y minus 3z is now equal to negative 6. And then you simply add these vertically. And so that's why this plus sign is here. So you do negative 3 times equation 1, which is just saying negative 3 times x plus 2z is equal to negative 3 times 6. So that's the negative 3 times equation 1 part. And then you simply add equation 2 to that. And what happens then, you get this new equation, and I'm going to put it right here. You're going to get 4y minus 9z is now equal to negative 24. All right, and that becomes our new equation 2. So that is our new equation 2. In a similar fashion, we're going to get a new equation 3. We're going to store it in the third row. So we're going to do negative 2 times equation 1 and then add it to equation 3. So we get 0 times x. And then we get negative y. So the first thing we see is negative y. And we need negative 4z add a 3z. Negative 4z add a 3z, we get minus z. And then we also have negative 12 add 5. Negative 12 add 5 is negative 7. All right. We're going to do one more thing. We're going to do one more thing here. We're going to do 4 times equation 3. We're going to do 4 times equation 3. And then add it to equation 2. And then we'll store it. We'll store it where? We'll store it in the second row. So we call it 2. Now, what's our first row? We're not even touching the first row. X plus 2z is equal to 6. That is our first row. Once we get 4 times equation 3 and add it to equation 2, what happens? Well, we get 0y, and then we get negative 4z minus 9z. So negative 13z. And then we also have negative 28 added to negative 24. So negative 52. Yeah. And then we did not change equation 3 at all. So equation 3 stays the same. I should draw another wiggly line here. There we go. All right. So equation 3 stays the same. Negative y minus z is equal to negative 7. So what I did was I end up working this idea of adding over and over again to eventually get down to one variable. And that is actually equation 2. We're actually going to take equation 2, and you could easily see that 13 is not 0. So if you divide both sides by 13, or negative 13, we get z equals 4. And then once you get one of the numbers, it's a lot easier to get the other numbers. So if you look at equation 3 from here, we can get y. That is going to be 7 minus y. Z is equal to 7 minus y. But we know what that is. That is equal to... Oh, why did I solve for z? I apologize. I meant to solve for y. Let me slow myself down. Let's solve for y instead. So I get 7 minus z. Y is equal to 7 minus z. Yes. And we already know z is 4, so this has to be 3. And then we go back to equation 1 to get our x. X is equal to 6 minus 2z. And we know what z is. Z is 4, so x is negative 2. So is there a solution to this system of equations? In fact, there's only one solution. And we're going to put that in a solution set. The solution set consists of one ordered triple. So there's only one solution, and that one solution is called an ordered triple. It's not only just one solution, it's actually what we call a unique solution. And what does the word unique means in mathematics? It just means one and only one. Unique just means one and only one. It is the one and only one solution to this system of equations. So this is the set consisting a unique solution.